The traditional reliance on vast agricultural landscapes for food production is facing a high-tech challenge from the laboratories of the Tianjin Institute of Industrial Biotechnology. Following a landmark breakthrough in 2021, where scientists first converted carbon dioxide into starch in a test tube, new reports indicate that researchers have now increased production yields by more than tenfold. This advancement moves the technology significantly closer to large-scale industrial application, potentially rewriting the history of human calorie acquisition. When the technology first emerged, the synthetic process was already 8.5 times faster than the natural synthesis found in corn. At that stage, a 3-ton fermentation tank could match the annual starch output of 1 hectare of corn land. Today, that efficiency has been further optimized. Given that starch provides 80% of the calories consumed by humanity and serves as a critical component in textiles, adhesives, and pharmaceuticals, the ability to manufacture it without soil or massive water consumption is transformative. The project, which began in earnest in 2015, effectively redesigned the biological process of photosynthesis. While plants require a complex 60-step process to create energy, the Chinese research team simplified this into an 11-step pathway. The process begins by using a catalyst to turn carbon dioxide into methanol, which is then converted by enzymes into sugar units and finally into starch that is molecularly identical to the natural variety. The primary hurdle remaining is the economic cost of production. Starch is a low-cost commodity, meaning synthetic versions must be exceptionally cheap to compete with traditional farming. To address this, the Institute established a dedicated research center in 2022 focused on the workhorse of the process, enzymes. Scientists are currently using artificial intelligence to screen for the most stable enzyme mutants and developing ways to reuse these enzymes multiple times rather than treating them as single-use disposables. If energy costs continue to decline and enzyme efficiency continues to rise, this technology could drastically reduce the need for pesticides, fertilizers, and arable land. Beyond starch, researchers believe the same carbon-to-sugar logic can be applied to fructose and sucrose, potentially securing food supplies while simultaneously utilizing industrial waste gases. What was a proof of concept a few years ago is rapidly becoming a viable industrial roadmap, bringing the world one step closer to a future where food security is decoupled from the unpredictability of the climate.